So let's do an example with conservation of angular momentum. Let's say that we've got a rectangular object here, and this rectangular object is spinning around its center of mass with an initial angular velocity of 21.5 radians per second. Let's say we call this object 1, and let's say that mass 1 is going to be equal to 6.25 kilograms. And we got, so this is M1, okay, we have dimension A and dimension B. So let's say that the width of it here is going to be 14 centimeters. And dimension B is going to be equal to 35 centimeters. Okay. Now, we then drop a hemisphere onto this thing. And the hemisphere, this will be object 2, is going to have a mass of, let's say it has a mass of 3.9 kilograms. It has a radius of 5.55 centimeters, and we drop it a distance d off center, so at 7.5 centimeters away from the center. Okay, and so what happens is when it drops onto that, then the mass is spinning, this drops, hits it, and now the two spin together, but now they have a different moment of inertia and therefore a different final velocity. So I want to know, what is that final velocity? Okay. Well, to do that, you recognize this as a collision problem. Okay. So you know that when we did collision problem before, that P initial was equal to P final. So now we're going to say that L initial equals L final. Okay. And so that's how we're going to do it. So what does this mean? It means that I initial times omega naught equals I final times the final omega. So I initial is going to be just I1, the I of the rectangular block. I final is going to be I1 plus I2. So while I initial is just the rectangular block here, then at the end, it's going to be a rectangular block with the hemisphere stuck to it. Okay. So all we got to do is find these i's, and then it's pretty simple. So omega is going to be I initial omega naught divided by I final. Okay. So I of the rectangular block. Okay. What's that going to be? Well, you look it up in the table. That's 1/12 mass a squared plus b squared. Okay. So it's 1/12 times 6.25 kilograms times 0.14 meter squared plus 0.35 meter squared. So I1 comes out to be equal to 0.074 kilogram meter squared. Okay. Now I want to know for the hemisphere off-centered from the center of the thing. Okay, so it's not landing center, it's landing off-center. I want to know what is that I. So this is going to be equal to I of the hemisphere plus mr squared. Okay, because remember parallel axis theorem. Okay, so you look up the for the hemisphere, the same as a sphere, 2/5 mr squared, okay, plus the mass times d squared. Okay, because we said that we call that distance d. All right, so that's going to be equal to 2/5 times 3.9 kilograms times 0.0555 meters squared plus 3.9 kilograms times 0.075 meters squared. And so I here now comes out to be 0.0268 kilogram meter squared. Okay, so now we had already derived it. Okay, so we said the final is going to be equal to the initial. Initial was just the I1 times omega naught, and the final is the combination of the two. Okay, so that's going to be equal to 0.074 kilogram meter squared times 21.5 radians per second divided by 0.074 kilogram meter squared plus 0.0268 kilogram meter squared. So the final omega is 15.8 radians per second. Now we could go one step further in all of this, and we could say what was the change in kinetic energy. Okay, so the initial kinetic energy would be 1/2 I1 omega naught squared, and the final kinetic energy is going to be 1/2 I1 plus I2 omega squared. Same as before. And you can actually do the calculations yourself here, and what you'll find is there's a net loss of kinetic energy. Just like there was a net loss of kinetic energy in an inelastic collision. In fact, what we're dealing with here is a perfectly inelastic rotational collision. So plugging in the numbers, you get that the initial kinetic energy was 17.1 joules. The final kinetic energy was 12.6 joules. So the change in kinetic energy, that's final minus initial, is a negative 4.5 joules. So we lost 4.5 joules. Where did this go? Energy does not just simply cease to exist in the universe. It became heat. Okay. And so warmed up slightly.